Hello everyone, and welcome to the last video of AP Calculus AB in 12 short videos. Today we are going to cover minima-maxima, Rolle's theorem, mean value theorems, and differential equations. These are all pretty easy, and as a bonus, the first three are tied together. All right, so first off, minima-maxima. So that is basically determining the minimum or the maximum value of a function. And the way you do that is at a vertex, which could potentially be the minimum or maximum value of a function, the derivative is always equal to 0. So we can use that to find the minimum or maximum value. All right, so now here's an example problem. So what value of x produces the minimum value of f of x equals x to the power of x? Well, to do that, you would find the derivative of the function and set it equal to 0. So first, finding the derivative, we can do that using implicit differentiation. If you remember how to do that, take the natural log on both sides and then differentiate both sides of the equation. And then in the end, you'll get that the derivative is x to the power of x times ln x plus 1. All right, and then now we set it equal to 0. So x to the power of x, it's not possible for that to be equal to 0. So the only possibility is ln x plus 1 is equal to 0. And then solving for that, we would get x equals 1 over e. So therefore, x equals 1 over e produces the minimum value of this function. So now here's a practice problem. And if you want to give it a try, then pause the video here and then keep watching for the solution. So here's the solution. So first we find the derivative of the function. So take the natural log on both sides and then differentiate both sides of the equation. On the right side, you can use the quotient rule. So it would be the derivative of ln x, which is 1 over x times x, and that just becomes 1 minus ln x times the derivative of x, which is 1. So 1 times ln x is ln x, and then over x squared. All right. And then now multiplying both sides by f of x, which is just x to the power of 1 over x, we get that this is what f prime of x is equal to. All right, and then set the derivative equal to 0 and solve for x. So x to the power of 1 over x cannot be equal to 0. You could argue that x equals 0 would work, but however, that means that the exponent is 1 over 0, which is undefined. So there are technically no values of x that satisfy this is equal to 0. So anyway, that means that the only possibility is this is equal to 0. So we solve, we get that x is equal to e. All right, so that means that x equals e produces the maximum value of x to the power of 1 over x. So now we're getting into Rolle's theorem. So there are three conditions. If f of x is a continuous function on the closed interval a comma b, and keep in mind that closed means it has to be continuous at a, b, and all values between, and f of x is differentiable on the open interval a comma b, and open means that it doesn't have to be differentiable at a or b, but it has to be differentiable at all values between, and f of a is equal to f of b, then there's at least one value c in the interval a comma b such that f prime of c is equal to 0. And the reason is because if all three of these conditions are satisfied, then there's at least one vertex. So here's an example. You see that there is a vertex here, and we know that at vertices, the derivative is equal to 0. So when is Rolle's theorem satisfied? So are the conditions of Rolle's theorem met in these functions? So first of all, f of x is equal to x squared for x in -1 comma 1. So yes, it does satisfy the conditions because the function is continuous on the interval -1 comma 1 because there are no abrupt jumps in value or values of x where the function is undefined. And second, it can be differentiated for any value x in the range -1 comma 1. And third, f of -1 is equal to f of 1 because -1 squared is the same as 1 squared. for f of x equals the absolute value of x for x in -2, 2, that does not satisfy the conditions, because even though the function is continuous on the interval, this function cannot be differentiated at x equals 0, because we see that right here, that from the left side, the slope is equal to -1, and from the right side, the slope is equal to 1. So since there are two conflicting answers, that means the function cannot be differentiated at x equals 0. For f of x equals 1 over x squared for x in -6, 6, that does not satisfy the conditions because the function is not continuous on the interval. There is a vertical asymptote at x equals 0. So this function is not defined at x equals 0. And finally, f of x equals the absolute value of cosine x for x in 0, 2 pi. That does not satisfy the conditions. This function is continuous. However, it cannot be differentiated at x equals pi over 2 or x equals 3 pi over 2 because we see the same problem as the absolute value function. From the left side, the slope is -1, and from the right side, the slope is 1. All right, so now knowing all of this information, here's a practice problem. So if you want, go ahead and try this by yourself. Here's the solution. So first we need to determine whether the theorem holds. So yes, because first of all, the function is continuous on the interval. There are no abrupt jumps in value or values of x where the function is undefined. Second, the function can be differentiated for any value x in the range -7, -1. And third, f of -7 is equal to f of -1. All right. All right, so Rolle's theorem holds. So now we need to find x equals c such that f prime of c is equal to 0. So we just differentiate the function. So we get 2x plus 8, and we set that equal to 0, and we solve that x equals -4. And this problem is asking for what is the value of c. So technically the answer should be c is equal to -4. So now we're getting into the mean value theorem for derivatives, because yes, there are two mean value theorems. So the conditions: if f of x is a continuous function on the interval a comma b, and f of x is differentiable on the open interval a comma b, then there is at least one value c in the interval a comma b such that f prime of c is equal to the slope of the line connecting the coordinates a comma f of a and b comma f of b. So here's an example. So we have a function, which is the red line, and we have a and b. And then we also have the y coordinates. So if we connect these two coordinates, then there is at least one value c between a and b, such that the derivative at x equals c is equal to the slope of the line that we just created. And the intuitive proof for that is you can rotate the graph so that it becomes a Rolle's theorem problem. So if you just rotate this, then it can become this right over here. And we already know that Rolle's theorem is true. So here's an example problem. And if you want, go ahead and pause the video and give this problem a try. And here is the solution. So the mean value theorem does hold. So first of all, the function is continuous on the closed interval -9, 16. This part's a little tricky because you could argue that it's not continuous at x equals -9 because on the left to the left of x equals -9, the function doesn't exist, and to the right, it does exist. So this is close to a jump in the value, but that's not true because we only need to consider values where the function does exist. So we only need to consider values where x is greater than or equal to -9. So that means that we do not need to consider values that are less than -9. So we don't need to consider the fact that to the left of -9, this function doesn't exist. So therefore, this function is continuous on the closed interval -9, 16. And then this function is also differentiable on the open interval. So the mean value theorem does hold. And to solve the second part of the problem, find the slope of the line connecting the coordinates and the derivative. So this is the function So the slope of the line connecting the coordinates is 1/5. And then the derivative, you can find that using the chain rule. You'll get 1/2 times the square root of 9 plus x. So now we set these equal to each other. All right, so then we solve for x. So multiply both sides by the denominators and then dividing by 2 and squaring both sides, you'll get this. And this is just 9. I changed it to a fraction. And if you solve, you get x is equal to -11/4 or -2.75. And the problem was asking for what is c. So the final answer should be c is equal to -2.75. And now we're moving into the mean value theorem for integrals. So if f of x is a continuous function on the interval a comma b, then there is at least one value c in the interval a comma b such that f of c is equal to the average value of the function on the interval a comma b. And the reason why that is true is because the average value in the interval has to be between the minimum and the maximum values in the interval. So in this case, the maximum is 4, the minimum is 0. The average value has to be somewhere between 4 and 0. And so since the function is continuous on the interval, we know that all values between 0 and 4 do exist on the interval. So for example, if the average value of the function was 2.25, then that would exist in this interval right over here. All right, here's an example problem. If you want, go ahead and pause and give this a problem a try. Here's the answer. So first we find the average value, and then so this was we just plug in the values into the formula. All right, and then you'll get this right over here. So this is just equal to 0. So we're left with 3. So that's the average value of the function in the interval 0, 3. All right, and now we set that equal to f of x and solve for c. All right, we'll get that x is equal to plus or minus the square root of 3. And remember, we're only concerned with values of c between 0 and 3. So negative square root of 3 is not between 0 and 3. So therefore, the solution is c is equal to the square root of 3. So now we're done. And now we're moving into differential equations. So differential equations relate a function to differentials. So your goal is to solve for the function or the set of functions that satisfy the equation. So here are some possible notations, and they all mean the same thing. So f prime of x is equal to f of x. That means what function is equal to its own derivative. You know that e to the power of x would work for f of x in this case, but are there any other solutions? Well, you can determine that using differential equations. So let's solve this differential equation right here. You can do that using separation of variables. Move all the y's and dy's to one side and all the x's and dx's to one side. So we can do that by dividing both sides by y and multiplying both sides by dx. So then on the left side, we only have y and dy. On the right side, we only have x and dx. All right, and now we integrate both sides. So if you remember the role of dy, the left side is ln of y plus c1. C1 is a constant. The right side is the integral of 1 times dx. You know that would be equal to x plus c2. And now we can subtract c1 on both sides. And on the right side, we would have an arbitrary constant minus an arbitrary constant. And that is still an arbitrary constant. So we can just change it to x plus c. And now if you take e to the power of both sides, you'll get y is equal to e to the power of x plus c. So e to the power of x is not the only function that's equal to its own derivative. You can also have e to the power of x plus 1, e to the power of x minus 2, basically e to the power of x plus any constant. So here's another example. We want to solve dy over dx is equal to negative x over y, given that f of 0 is equal to 2. So first, let's forget that f of 0 is equal to 2 and solve this differential equation. So we move all the dy's and y's to one side, all the x's and dx's to the other side. All right, we multiply both sides by y and dx to do that. and then integrate both sides. So the left side becomes y squared over 2, right side becomes negative x squared over 2 plus c. Remember, we only need a constant on one side. All right, adding x squared over 2 on both sides and multiplying by 2. So on the right side, you should have 2 times c, but 2 times an arbitrary constant is still an arbitrary constant, so we can just leave it as c. All right, so if we weren't given that f of 0 is equal to 2, then this would be the answer. But since we're given that, we need to solve for c. So we plug in 0 for x and 2 for y. We can solve that c is equal to 4. So the final answer is x squared plus y squared is equal to 4. All right, so now knowing all of this information, here's a practice problem. If you want, go ahead and pause and give this a try. Here is the solution. So move all the dy's and y's to one side, all the dx's and x's to the other side. So you can do that by multiplying both sides by dx and dividing both sides by y. So on the left side, you get 1 over y times dy. On the right side, you have 1 over x squared, which is just x to the power of negative 2. All right, integrating both sides. On the left side, you have ln of y. On the right side, you can use the power rule where the exponent is just negative 2. You'll get negative 1 over x plus c. And then taking e to the power of both sides, you'll get y is equal to e to the power of negative 1 over x plus c. And that's our final answer. All right, here's another practice problem. And here is a solution. So so multiply both sides by cosine y plus 1 and dx. All right, and then integrating both sides. So the left side becomes sine y plus y is equal to x squared. And then the right side becomes x squared plus c. All right, since you're given that f of 1 is equal to 0, you need to solve for c. So you plug in x is 1 and y is 0. So the left side just becomes 0. And then subtracting 1 on both sides, you'll get c is equal to negative 1. So the final answer is sine of y plus y is equal to x squared minus 1. So what are some real world examples? Well, here's an example. A car's speed is inversely proportional to the square of the distance traveled. And let x represent time, let y represent distance, and let k represent the constant of proportionality. Write and solve a differential equation for this situation. All right, so the way we do that is you need to know that speed or velocity is the derivative of distance with respect to time, and acceleration is the derivative of speed or velocity with respect to time. So these two facts are actually pretty important for AP Calculus AB, so remember them. And there is a difference between speed and velocity, but you don't need to know that. So anyway, we're told that the speed, which is just the derivative of distance with respect to time, is inversely proportional to the distance squared. So that means that it's just equal to the constant of proportionality over y squared. So this right over here is our differential equation. And solving, you can multiply both sides by y squared and dx. Integrating both sides, on the left side, you have y cubed over 3 is equal to, and then, well, we have the integral of a constant times dx, and we know that would just be the constant times x, all right, and then plus c, and then multiplying both sides by 3. Remember, an arbitrary constant, you don't need to multiply that by 3. And then taking the cube root on both sides, you'll get that this right over here is our final answer. So congratulations, you have finished the course AP Calculus AB in 12 short videos. In the description, I will put a number of useful links, so I suggest you check it out. For more educational opportunities, visit scapenext.org. We offer a variety of free YouTube and Zoom courses. So you've just finished one of those courses, and there are many examples of other courses that we offer. Finally, subscribe. That will have two impacts. One, you will be notified whenever new educational content is posted. And two, you will increase my motivation to post educational content. So by subscribing, you are benefiting yourself. But anyway, that's the end of this video. So I hope to see you in my other courses.